Alrighty, folks. Today we are going to be covering chapter 2 in your textbook, and we're going to be covering it pretty much in its entirety. And so that should be pretty good. Chapter 2 covers the idea of limits. As we start thinking about calculus, calculus focuses primarily on the idea of rates of change, but in order to formally define what rates of change means, we need to have limits. And here's the broad strokes for what a limit is. And so have you ever had a problem where there's a value that's undefined and you think to yourself, yeah, but if it was defined, I know what it would be. Well, that's what limits are all about. And here's a simple example. Consider the function f of x equals x squared minus 4 over x minus 2. And the question is, what happens when x is equal to 2? Now, there's a few ways we can think about this. Initially, we can just think what happens when we plug 2 into the equation. And we get something which is undefined. We get 0 divided by 0. And so automatically we know we cannot plug 2 into this equation. But when we think about limits, well, again, limits are saying, what if it were defined? And so what if we look at the graph? I have the graph of it here, and notice when we're looking at 2, the value is actually very, very close to 4. Desmos actually doesn't even recognize a hole there unless you click on that point. And so it looks like it should go through the point 2, 4. We can then do a table of values. And so here's a simple table of values. At 1.9, we get 3.9. At 1.99, we get 3.99. As we continue at 2.001, we get 4.001. It really looks like at 2, we should be getting something very close to 4. A final approach we can take is algebraically. If we think of x squared minus 4 over x minus 2, well, that's the same as x plus 2, x minus 2 over x minus 2, which is equal to x plus 2. And x plus 2 would give 4 when you plug 2 into it, because 2 plus 2 is 4. And so even though we know that it's undefined at that value, if we were asked what the limit is, or what the limit is as you approach 2, we would say that it is 4. And this is what that looks like in symbols. The limit as x goes to 2 of x squared minus 4 over x minus 2 is equal to 4. And that's our big picture for what limits are all about. It's all about what happens as you get arbitrarily close to some value. If the value is undefined at that point, it's okay, because limits are just asking what value should go there. And there's also the question of what happens as you go for a very, very long time. We can't plug infinity into a function, but what happens as you go to infinity or negative infinity? Or what happens as we're approaching an asymptote? These are questions which we can ask, and up to this point, we've mostly said, well, the answer is undefined because we can't plug that in. But now we have a way of actually exploring these ideas. And so your textbook starts with the idea of the limit of sequences. Personally, I view the limit of functions as being much more valuable, because when you're talking about functions, we know functions. Sequences, for some folks, it's going to be a fairly new idea. A sequence is really just a list of numbers that goes on and on and on forever and ever and ever. And so a sequence a sub n has the limit L if we can make the term a sub n as close to L as we like, by taking n to be sufficiently large. That's a fairly formal definition. What it really means is as you go to infinity, what is this sequence getting arbitrarily close to? What single number is it getting arbitrarily close to? If it's bouncing back and forth between multiple numbers, we would say the limit does not exist. But if, as you go on for a very, very long time, it gets ridiculously close to a single value, then we would say that the limit exists. In this case, we would say the sequence converges if the limit exists, and a sequence diverges if there is no such limit. And let's just jump into a few practice problems real quick and see if we can figure out what these look like. And so the first one is a sub n equals negative 1 to the n. And I'll stop the share. And the question is, does this sequence have a limit? And feel free to pause the video and answer the question, but let's jump right into it. The easiest way to think about something like this is to just start plugging in some values so that we can understand what the sequence is doing. And so instead of doing the standard x and y, we'll say n and a sub n. And so for instance, when n is 1, we're going to get -1 to the first power, which is -1. At 2, we get -1 squared, which is 1. At 3, we get -1 cubed, which is -1, and so on. Now, when we think about sequences and we're trying to figure out what the limit of the sequence is, we don't really care about the small numbers. This is more just to give us some idea of what's happening with this function or with this sequence. And in this case, we can see that it's going back and forth between -1 and +1. So -1, +1, -1, +1, -1, +1. And it's going to continue that pattern forever and ever and ever. And so in this case, it's not going to be approaching a single value. And so the limit as n goes to infinity of this function, a sub n, I guess this sequence, which we could say is -1 to the n, does not exist. This diverges. And that's really all there is to this idea. We can just try and figure out what the long-term behavior is. The challenge is there isn't one set approach for these problems. And we'll see a wide variety of different approaches. And so let's look at the second one. Number 2. That was number 1. Number 2 is a sub n is equal to 1 over n plus 4. And again, the question is, what is the long-term behavior of this sequence going to be? And again, we can create a little chart like this if we want to. N and a sub n. We could say what happens at 1, 2, 3, 4, and so on. Well, at 1, we're going to get 1 over 1 plus 4, which is 5. At 2, we're going to get half plus 4, which is 4.5. Then 4 and a third. Then 4 and a fourth. And so on. If we continue this pattern, we'll get something like, how about at 100, it would be 4 and 1/100th. And so the question is this sequence going to be approaching a single number? And in this case, it is. The limit as n goes to infinity of 1 over n plus 4 is going to be equal to 4. That's our answer. In this case, it converges to 4. The next one kind of combines those two, and let's see what that looks like. So our third example is a sub n is equal to 12 times -1 to the n over n plus 1. Now for this one, let's not create the table, and let's see if we can just understand it based on the structure of this thing. Oftentimes when we're looking at calculus ideas, we want to understand the structure of a function, or in this case, the structure of this sequence. And so looking at this, we have the 12 in the front. That's considered a scalar. It's something which is multiplied by the main function. We then have the -1 to the n. The -1 to the n, we already know the behavior of that. -1 to the n is going to be going back and forth between -1, +1, -1, +1, and so on. And so that might be a red flag that this diverges. But we also want to see what the n plus 1 is doing. The n plus 1, as n gets super big, is going to become super large. And so that means that our denominator is going to get huge. If we think about it, as n goes to infinity, well, when n is equal to 1 million, this is going to be 1,000,001. So the denominator goes to infinity, let's say. Well, as our denominator gets larger and larger and larger, this is going to become a fraction with a much larger and larger base. And so looking at this 12 times -1 to the n, the -1 to the n might be oscillating, but this denominator is going to get huge. And so if we were to think of the graph of this, it might look something like this. And notice it's going back and forth to others, or each time you're going further on down the road, but it's still getting very, very close to 0. And that's really what the limit is going to be for this one. Even though it's oscillating, this denominator means that the entire thing is going to be going to 0. It's just going to be bouncing back and forth until you hit 0. And so in this case, the limit, as n goes to infinity, of 12 times -1 to the n over n plus 1, it's going to be equal to 0. This function converges. The next 3 problems are very, very similar, and they're good to get practice with, just to try to understand again how we might dissect a sequence or a function. And so let's write all 3 of these real quick. So the first one is going to be a sub n is equal to 4n squared plus 3n over 2n squared minus 11. The next one is a sub n equals 4n squared plus 3n over 2n minus 11. And the third one, a sub n is equal to 4n squared plus 3n over 2n cubed minus 11. So again, the question becomes, what is the long-term behavior of these 3 sequences? And the only difference between these 3 sequences is the exponent on this bottom term. This one's got it squared, this one is just linear, and then this one is cubed. And let's see how that affects each of these functions, or each of these sequences. Again, I keep going back to the idea of these being sequences because we're going to be seeing, as functions, because we're going to be seeing a lot of functions. And so for this first one, what you really want to ask is you really want to ask which terms actually matter as we get to super large numbers. And we're not talking about thousands or millions. We're talking about a trillion, trillion, trillion. Or what about 10 to the 2000th? That would be a 1 with 2,000 zeros after it. When you get to numbers which are that large, we can look at our sequence and ask which terms don't matter. For instance, even at 1 million, if we have 2 times 1 million squared minus 11, that minus 11 is not really going to be bearing a lot of weight on this fraction, because we would get 2 trillion minus 11, which is still really close to 2 trillion. And so when we're analyzing the structure of this one, we can ignore that 11. Same in the numerator. If we're at 1 million, well, 4 times 1 million squared would be 4 trillion. And 4 trillion plus 3 million is still very close to 4 trillion, because 1 million is 1/1,000,000th of a trillion. And so for the numerator, the 3n really bears no weight on what's happening with this sequence. Looking at this now, though, we're saying that for very large numbers, we're going to be left with something that's close to 4n squared over 2n squared. Well, 4n squared over 2n squared is going to be 4 over 2, which gives us 2. And so for this one, the limit as n goes to infinity of this sequence is 2. We can do the same trick with this middle one. And so again, ask what happens when you are at really, really big numbers. And so looking at the denominator, if you are at 1,000,000, we're going to get 2,000,000 minus 11. That minus 11 has almost no effect on this fraction. Same in the numerator. 4 million squared would be 4 trillion plus 3 million. This 3 million here has no bearance on this fraction. But now, as we get to very, very large numbers, we get 4n squared over 2n, which we could simplify to give us 4n over 2, or just 2n. Well, as n gets to be a super large number, this is going to become an even bigger number, because this is always going to be approaching twice whatever your n value is. When we're at 1,000,000, we would expect this to be close to 2 million. When we're at 1 trillion, we would expect this to be close to 2 trillion. And so this sequence, limit as n goes to infinity of a sub n, is going to go to infinity. This diverges because it goes off to infinity. Same logic for this last one. And so for this last one, 4n squared plus 3n, 2n cubed minus 11. Again, these terms do not matter for the long-term behavior of this function, which means that we are going to be simplifying this to 4 over 2n, which is, again, going to be 2 over n. This was approximate. 2 over n, as n gets super large, is going to give us 2 over a very large number. And 2 divided by a very large number is very close to 0. And so in this case, the limit as n goes to infinity of a sub n is equal to 0. So notice, while these three looked very similar, the structure of them was different enough that we got substantially different answers from them. We managed to get a nice number out of this one. This one went to infinity, and then this one went to 0. And so you want to be careful of things like exponents when you're trying to analyze the structure of these objects. We have a lot of rules for sequences, and these are more kind of guidelines that'll make it easier for you. If you are taking the limit of a sum, turns out you could take the limit of each piece individually and then just add them together. Same with differences. Same with scalar multiples. And so if you said the limit as n goes to infinity of c times an, we could just factor that c out. And so that one that had the 12, we just pulled the 12 out and it didn't matter. The limit of a constant remains a constant. The limit of the product is equal to a product of the limits. Same with the quotients, and same with exponents. And so really limits work the way you would think they would work. And hopefully that works to our favor. Now, if you recall, last time we talked about recursive sequences as well. We can find the limit of recursive sequences just the same as we can find the limit of typical sequences. And so when we have a recursive sequence, we might have to do a little bit of algebra in order to figure out what the long-term behavior is. And so here's a sample problem. This is one which I always like to go to. A drug is administered to a patient at the same time every day. Suppose that the concentration of the drug is C sub n, measured in milligrams per milliliter, after the injection on the nth day. Before the injection the next day, only 30% of the drug present on the preceding day remains, in the bloodstream. If the daily dose raises the concentration by 0.2 milligrams per milliliter, what will the concentration be on day 4? What will the concentration be as n goes to infinity? And so this is a nice one to model out and actually have the solution written right beneath it. And so looking at this, since we're saying that only 30% of the drug present the preceding day remains, this tells us that we're going to be multiplying by 0.3. If the daily dose raises the concentration by 0.2 milligrams per milliliter, that means each day we're going to be adding a 0.2. And so we get this model out of it. C sub n is equal to 0.3 C sub n minus 1 plus 0.2. And C naught is equal to 0 because you start with none of the drug in your system. We could have written this as C sub n plus 1 and made this a C sub n. That would work just the same. In order to calculate the different days, well, when we take 0 and plug it in here, we get 0.3 times 0, which is 0, plus 0.2. And that gives us 0.2. We can continue that to figure out the first 4 days. And so to figure out the first 4 days, we're just plugging in the prior day into this, and we get the next day. And so 0.2 comes in, and then we plug it in, and we get 0.26. We take the 0.26 as the input for day 3, and then day 3, we end up getting 0.278. And then we take that and we plug it in, and we just continue this pattern over and over and over again. The question is this approaching some number, or is it going to go off to infinity? And looking at it, it doesn't look like it's getting that large. Now, if you think about it, if your body is processing this amount, it's not going to go to infinity, because if it did, that would mean you would have an infinite amount of a fluid in your body, and that's not really possible. The trick for this, to figure out the long-term behavior, is to suppose that this C sub n and C sub n minus 1 end up approaching the same value, which I think I just call C here. Yeah, and so suppose that C is equal to the limit as n goes to infinity of C sub n. Well, if we plug C into this equation, then we would get C equals 0.3 C plus 0.2. And that's what we have here. C is equal to 0.3 C plus 0.2. This is a linear equation. We can solve it. Multiply everything by 10, move the 0.03 C over to the left side, and then divide. You'll end up getting 2/7, which is 0.285714 with a bar over it. And so the limit for this, what we expect the concentration to approach as n goes to infinity, is 0.285714 over and over and over again. And so that's a nice thing about this. This is the underlying principle for most injections that you get. If you get an injection periodically, then this is how we can calculate it. And if the drug is only effective during a certain window, you can use that window to calculate how much or what concentration you need to be injecting in order to maintain that particular ratio. And so that's kind of a big thing. Eventually, we'll start talking about how a drip line works mathematically, but that comes in chapter 6, I think. The next topic is one which we'll just kind of gloss over. It's the idea of geometric sequences and series. Your book talks a little bit about it. You have a couple of problems in your homework about it, but there's nothing too special about geometric sequences and series, except that their solutions are a little bit easier to find. And so, for instance, if we look at a geometric sequence, it's always going to be of this format, a times r to the n, where r is some number, and basically, for consecutive values, you're just multiplying over and over and over by the same value. And so for this first example, if we multiply by 1/2, each time we go 40, 20, 10, 5, 5 halves, on and on and on. Looking at this one, it's multiplying by 3 each time. And so 5/12 times 3 is 5/4 times 3 is 3.75, and so on, all of the way down. Notice this first one converges. It goes to 0. This one diverges. It goes off to infinity. And those are the two cases for geometric sequences. It's always either going to go to 0 or it's going to explode out to infinity. Unless you're talking about negative numbers, in which case it could go back and forth to infinity and negative infinity. One thing that is interesting, though, is sometimes you add up all of the elements of a sequence. And when you do that with a geometric sequence, it turns out you get something fairly nice. And so a geometric series is a recursive sequence for which we add the terms of a geometric sequence. And so we would go from 40 to 60, because we would do 40 plus 20 is 60. And then we would add 10, which would give us 70, and then 75, and then 77.5, and then just continue on and on and on. And the question becomes, does it approach some value? Does it converge or diverge? Well, it turns out we have formulas for it. And so if you ever want to add up the first n elements of a geometric sequence, this is what the answer is always going to be. It's always going to be a times 1 minus r to the n plus 1 over 1 minus r. It turns out you can find the limit as well. The limit as n goes to infinity is always going to be given by s sub n, or the limit is equal to a over 1 minus r, where the a and r are coming from these values. So in this case, the a would be 40, and the r would be 1/2, because it's multiplying by 1/2 each time. That said, there's nothing really that interesting about this other than that we can get a concrete solution for it. If you were taking Math 401, Math 401 is Calc 2. And what's special about Calc 2 is it focuses a lot on the idea of sequences and series. And in that course, geometric series is one type of series, but there's another 20 different types of series out there that you would be analyzing. I mean, you'd be trying to determine if they converge or diverge. And most of them are so difficult that you can't actually compute them. Geometric series, it's nice because you can actually compute them. But for our purposes, for a calculus for biology and medicine, it's something neat, but it's not something that you're going to be using that often. And so you'll see a couple of these in the homework where you're really just asked to plug stuff into these formulas, but don't lose too much sleep over it. Now we're getting to some fun problems. And so infinite limits of functions. Infinite limits of functions work exactly the same way as the infinite limits of sequences. There's next to no difference. The only real difference is with a sequence, you're talking about discrete numbers. With a function, it's continuous numbers. And so everything on an interval needs to be continuously going towards some value. There's a lot of interesting things that can happen with these. And let's just start playing with them and see if we can figure these things out. Again, feel free to pause the video, and if you want, try and work through all of these. They should all be fairly doable. And then we'll work through them together real quick. And so let's start with number 1. And so 1 is the limit as t goes to infinity of 1 over t plus 6. I'll stop the share and we will work through this one. Then we'll work through all of the others as well. And so with this one, again, you want to ask what happens when t gets really big, because that's what t going to infinity means. It means that t is becoming a very large number. And as t becomes a very large number, like a million bajillion, this becomes 1 over a million bajillion plus 6. And having a super large denominator means that this fraction is becoming tiny. And so the long-term behavior of this is that this is going to go to 0. Done. That's the nice thing about these. If you understand your functions and you understand the structure of your functions, these problems can be very intuitive, and there's not going to be a lot of work to actually show for them. Number 2 is very similar. Limit as t goes to negative infinity of 1 over t plus 6. So now instead of going to the right, we're going to the left. And so thinking about what this graph looks like, this is a function which has been shifted left 6 units. And so it would look something like this. And so as we went to the right, the limit approached 0. What happens is we approach it to the left. Well, on the left, notice it is still going to 0. And so the answer is still 0. Note that what this would look like. So this is talking about the t value going to infinity. That means as we're going to the right. But this right here, this 1 over t plus 6, or this 1 over t plus 6, that is the function, which means that's corresponding to the y value. And so the y value is what's going to 0 here. The third example we have, number 3. The limit as x goes to infinity of 9 plus 5x minus 4x squared over 3 minus 7x plus 6x squared. Now with this one, there are 2 approaches. One is the approach that we've already seen, and it's a great approach. Oh, it makes it so quick. Because with the approach that we've already seen, really we're just looking in the numerator and the denominator and saying which values matter and which ones don't. As we approach infinity, this 9 does not matter. The 5x does not matter. And the reason those 2 don't matter is because this negative 4x squared is going to become so monumentally large as we go to infinity that it's going to make these other 2 terms look extremely small. Same in the denominator. The 3 and the 7x do not matter for large values. And what we're left with is negative 4x squared over 6x squared for large values. And that reduces to negative 2/3. And that's our answer. There is an algebraic approach for this one. And so let's take a look at the algebraic approach for this one. The other way that we could do this, and I'll write it over here, is limit as x goes to infinity of 9 plus 5x minus 4x squared over 3 minus 7x plus 6x squared. And this is the way your book will show you how to do this one. What it'll recommend doing is it'll recommend dividing by the largest exponent. And so looking at these, we have x squareds floating around. And so we could divide each of these by x squared. The reason we do that is because now we can look term by term and say, what happens as x goes to infinity for that particular term? And so as x goes to infinity, 9 over x squared goes to 0. 5x over x squared also goes to 0. Negative 4x squared over x squared goes to negative 4. This goes to 0. This goes to 0. This goes to 6. Combining the top, we get negative 4 over 6. And then that leaves us with the negative 2/3 again. This approach here is an algebraic approach because we used algebra in order to figure it out. And so we simplified everything using algebra. This first approach we did was an analytic approach. because we used analysis. We analyzed the structure of the function to figure out which terms actually mattered. Those are going to be the two main approaches that you use, either algebraic or analytic. And sometimes it helps to think of it as these two separate approaches. I personally will try and use the analytic approach whenever possible because I feel very, very comfortable with my functions. And if you feel very comfortable with your functions, it'll save you a lot of time if you can avoid doing all of the algebra for every problem. The fourth problem we have is the limit as x goes to infinity of sine of x. And hopefully with this one, you can kind of figure out the answer pretty quick. As x goes to infinity, sine is going to be going back and forth. The graph of sine, if you remember, goes up and down and up and down. There is no single value which this is going to approach. And so this limit does not exist. Typically, when you are answering limits problems, there are 4 different answers that you can get. With the sequences, it was converge or diverge. But when you're actually trying to figure out computationally what these things approach, you'll either get a number, or you'll get infinity, or you'll get negative infinity, or you'll get does not exist. These are the 4 answers that you will be seeing. The infinity one, that one converges. These other 3 diverge. The infinity means that everything is going to be going and getting larger and larger and larger. The negative infinity means that it's going to be going to negative infinity. And the does not exist means something else is going on. Frequently, what it means is that it'll be somehow bouncing between the 2. Or it'll just be oscillating in some way, or maybe there's some weird behavior going on. Does not exist is really just the catch-all. And sine of x, it doesn't go to infinity, it doesn't go to negative infinity, it just oscillates. It just has no value that it approaches. The next 2 are dealing with e to the x, or e to the t. And so the limit as t goes to infinity of e to the t. And then we'll say the limit as t goes to negative infinity of e to the t. And then we'll say the limit as t goes to infinity of e to the negative t. And then we'll do the limit as t goes to negative infinity of e to the negative t. This one wasn't included and it had x's instead of t's, but they're all the same. And so let's calculate these real quick, but let's actually use a different tool. And so let's use our good friend Desmos. And so pulling Desmos up, what we can do is we can graph these functions. And so let's say f of t is equal to e to the t. The first question we had, the limit as t goes to infinity of e to the t, asks what happens as you're going to the right on this graph. And as you go to the right on this graph, you're going to be approaching infinity. The limit as t goes to negative infinity, well, that's going to be saying what happens as you go to the left. And as you go to the left, we know this is going to approach 0. For the reflection of this one, where we have a negative t, the limit as t goes to infinity now is going to be 0. And the limit as we go to negative infinity of this function is again going to be infinity. Because as we go to the left, this function gets monumentally large. Understanding the structure of these functions is going to be imperative. And that's why you really need to feel comfortable with that laundry list of functions that we talked about last time. You need to make sure that you know what the graphs of all of those functions are and what their behavior actually is, because we're going to be playing with those functions the entire semester. The next one is kind of an interesting one. So now we are up to question number 9. And now we're starting to see the types of things that we're going to be dealing with the entire semester. So number 9 says the limit as t goes to infinity of e to the negative t times cosine of t. This is the product of two functions. And what we want to do is we want to figure out what happens as this thing goes to infinity. We know that cosine is going to be oscillating. We know that e to the negative t is going to be going to 0. And so what would the graph of this function look like? And if you don't know, plug it into Desmos. Here's a quick sketch of what it's going to do, though. We know that the cosine is going to be oscillating, and we know that the e to the negative t is basically going to be working like the amplitude of that function. And so it's going to be looking something like this. On the other side, it'll go crazy. And so as this goes to infinity, it's going to get squeezed down to 0. Because it has to be bound between e to the negative t and negative e to the negative t, because that's what the amplitude is. And then the cosine, it'll oscillate, but it's still going to be approaching 0. Number 10 is a little different. So 10 says, what's the limit as t goes to infinity of e to the negative t plus cosine of t? So now instead of multiplying, they're being added together. And so when we add these together, something weird happens. The graph of this, if we were to graph it, well, e to the negative t, as we're going to the left, is going to get monumentally large. And we already know that. What the cosine would do, though, is it would oscillate, but it's going to be bounded. It would stay between -1 and +1. And so we can keep that in mind and say that the -1 to +1 is not going to really affect much of the graph. On the right side, however, it's going to be substantially different. Because on the right side of the graph, e to the negative t is going to get really, really, really close to 0. But cosine of t, it's going to be oscillating back and forth between -1 and 1. What happens if you take 0 and you add it to something between -1 and 1? Well, you just get that something between -1 and 1. And so the curve for this is actually going to start looking like the e to the negative t on the left side. But then as you get to the right side, we're actually going to get something which oscillates and starts looking kind of like a cosine function. And it's not going to approach 0. It's going to look very, very similar to a cosine function. Just to prove it real quick, let's pull up our good friend Desmos. Share screen. And so if we were to do e to the negative t plus cosine of t, notice how on the left it looks like an exponential, but on the right side it turns into a cosine. And that's because the exponential, it adds next to nothing over on the right side because it gets so small so fast. And so does this have a limit? The answer is no. The limit does not exist. It is oscillating. The next one, number 11, it's interesting again. Again, limits are very fun. They're worth playing with. And so the limit as t goes to infinity of cosine of t over e to the t plus cosine of t. And so again, we want to think about the long-term behavior of this. And so the long-term behavior of this function, we know that the cosine of t is going to be bouncing back and forth between -1 and +1. Same with this one. The cosine of t is going to be bouncing between -1 and +1. But e to the t is going to get monumentally large. And so analyzing the structure of this function, we have something that remains bounded between -1 and 1, divided by something which is going to be going to infinity, because infinity plus -1 to 1 is still infinity. And since we have something finite in the numerator and something infinite in the denominator, this is going to go to 0. Again, I might recommend plugging this into Desmos to see what it looks like. And so our good friend Desmos, when we graph this thing, we get the cosine of t over e to the t plus cosine of t. Notice we have some interesting behavior on the left side, but on the right side, we don't have nearly as interesting behavior. It just goes to 0 very, very quick. E to the t is a very fast function, which means that it goes to 0 almost immediately. But you might be wondering what's happening on the left side. And let's try a similar problem to see what happens on that left side. And so instead of doing this problem, I'm going to change one of the signs. And so let's do this one. The limit as t goes to infinity of cosine of t over e to the -t plus cosine of t. And so with this one, it looks kind of similar. We can do the same type of analysis. This is going to be going to something close to -1 to 1. This one is now going to be going to 0. And this one's going to be going to -1 to 1. And so when we try and figure out what this behavior is going to look like, you might be tempted to say this e to the -t does not matter because it goes to 0, which would mean we would get cosine over cosine, and cosine over cosine is equal to 1. However, that's wrong. The reason that's wrong is because you have to keep in mind what number's between -1 and 1. That number being 0. This function is going to be dividing by 0 an infinite number of times as we go out to infinity. Moreover, since this e to the -t is close to 0, but not exactly equal to 0, we're going to get a behavior where we're going to get a graph like this. And so most of the time, the graph is going to be close to 1. But every pi or so, we're going to get something that does something like this. And I might have it flipped, but it looks something like this. And then again, these values here are where the denominator is equal to 0. And the denominator is going to be equal to 0 an infinite number of times. Desmos has a hard time showing that, though, because of how zoomed in you'd have to be to actually see that behavior. And so let's share the screen and I'll show you what I mean. If we make this an e to the -t, notice it shows the behavior here, and I was again wrong with the directions of the asymptotes. it comes down, goes up, it goes up, and then here it goes down, and then it goes down, and then over here, if we look really close, it goes up. But you have to be zoomed in quite a bit to even see this. If we were out further, Desmos has a hard time actually showing that there is this asymptote. But these asymptotes do exist, and they exist all of the way down. Yeah, there's another one. But notice how zoomed in you would need to be to really see that. And so Desmos is a great tool, but you have to understand the structure of these functions in order to be able to use it effectively. Let's see, the next one, square root of x squared plus 1 minus x. Again, you could kind of ask the question, what's the long-term behavior going to be? And if you are at a million bajillion, you're going to get the square root of a million bajillion squared plus 1 minus a million bajillion. Well, the square root of a million bajillion plus 1 squared is a million bajillion. And so it's a million bajillion minus a million bajillion, which tells us that this is going to be approaching our good friend 0, because this term and this term are very close to one another. The next one, the natural log of x. As x goes out to infinity, well, we know what the graph looks like. Let's see if I can make it so that it goes home. Y equals the natural log of x. In this case, it is a very, 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 very slow function. And it doesn't look like it's getting much larger, but it is very slowly getting larger. Natural log is one of the slowest functions out there, but it will still go out to infinity. And so the y value will eventually get as large as we need it to get. And so for the limit as x goes to infinity of natural log of x, that one is infinity. Let's do the last one here. The limit as x goes to infinity of 4x squared plus sine of x over e to the negative x plus 8x squared. So again, let's analyze the structure of this function. And so the 4x squared, we know that the 4x squared is going to be going off to infinity. The sine of x, we know that that's going to be remaining bounded between -1 and 1. E to the negative x, we know is going to go to 0. And 8x squared, we know is going to be going to infinity. And so when we are looking at the long-term behavior of this, only 2 of the terms actually matter. And that's the 4x squared over 8x squared. Still, we should include the limit as x goes to infinity in there. But now reducing this, we get 1/2. And so as x goes to infinity, we would expect this function, which has a trigonometric, an exponential, and 2 quadratics in it, to go to 1/2. And if you want, you can graph it. I'll let you play with Desmos this time around. But this is the type of function which we're going to be playing with. Notice that this has multiple functions within it. This is a rational function, but it's a composition of 4 different types of functions. And so definitely make sure you feel comfortable with each of those individual types of functions. We also have the idea of a horizontal asymptote. If a line has if a function has a limit, that limit is a horizontal asymptote. And it could be at infinity or at negative infinity. It would still be considered a horizontal asymptote. And so you'll see lots of functions which have multiple asymptotes, multiple horizontal asymptotes. Though the most you can really have is 2, one in the positive direction and one in the negative direction. We also have limits at finite values. And so far we've been focusing on limits at infinity. But when we think back to the first problem we did, it was a limit at a finite value. It was a limit at a single digit, a single number, rather than looking for the long-term behavior. When we think of limits at finite values, really we want to think about left-hand limits and right-hand limits. And so the idea of a left-hand limit versus a right-hand limit is what happens as we're approaching from one side as opposed to the other side. Let me draw it out real quick. And so let's suppose that we have a function which looks like this. Let's say that it comes up here, it's defined here, and then it jumps down here. Let's say that this value is called t. We'll call this a, and we'll call this b. Then for the left-hand limit, the left-hand limit is what happens as you are coming from the left side. And so in this case, the limit as x goes to t from the left side, and so we use the minus sign to represent the left side of this function, f of x, is going to be equal to the b value. For the right-hand limit, you can probably guess the limit as x goes to t from the positive side of this function is going to be equal to a. Notice in this case, if we were to actually calculate what f of t is, f of t in this case is b. Doesn't have to be. Had we had this be an open circle, we could have had another point up here if we wanted to. Call that c. And sometimes you'll see functions like this, where the left side and the right side don't match, and neither one of them is actually the same as your starting value, or what value you'd get if you actually plugged things into it. To calculate the actual limit, though, the actual limit only exists if the left and the right match up. And so the limit as x goes to t is equal to L. Oh, well, I guess I should write it all out. So let's say the actual limit of the function is equal to L if and only if the left-hand limit of the function is equal to the right side, or the right-hand limit. And in that case, whatever value you get is going to be the limit. For this example, there is no limit because the limit from the left does not equal the limit from the right. If the limit from the left equaled the limit from the right, then we would say that it has a limit. So let's look at this second example here, because I think this second example will demonstrate this a little better. And so for this one, let's even put it into Desmos real quick. And so it's the limit, or it's x minus 1 squared, y equals x minus 1 squared. And I believe that it was on the interval up to 1. Yeah, and so this is on the interval up to 1. And then we have the point 3 when x is equal to 1. And so in our good friend Desmos, we could just say 1 comma 3. And then our third point is, or our third line is 2x minus 2. 2x minus 2 on the interval from 1 to infinity. And so this is what the graph looks like. Technically, there is a hole down at the bottom. And so let's see if I can actually graph that. I believe it would be at 1, 0. And then we would want to make this, will it not let me? There we go. So this is what the graph looks like. There we are. Make it a little bit larger. As we look at this, the limit as we are coming from the left is going to be equal to 0. The limit as you are coming from the right is going to be equal to 0. And that tells us that the limit is 0. And so in this case, the limit as x goes to 1 of this function is equal to 0. Notice though that f of x, or f of 1, is actually equal to 3. Your limit does not necessarily reflect what the actual value of the function is. So down here is our limit. Up here is the actual value. It is okay for these things to be different. We also have the idea of infinite limits, and I kind of mentioned that earlier when I said that we could have a limit be a number, infinity, negative infinity, or does not exist. If the limit as you approach a number goes or becomes arbitrarily large, then we would say that that limit is infinity. If it goes to a negative large number, then it's negative infinity. And we say that those values give us vertical asymptotes. And here's some practice problems. Let's see what we can do with them. So for this first one, the limit is t goes to 5 of t squared plus 2t minus 3. And again, I'd encourage you to pause and try all of these problems real quick. T squared plus 2t minus 3. So for this first one, really what you should ask is, can I just plug the number in? And if you're able to, you can probably get away with it. We consider these functions continuous functions because there's nothing weird going on with the domain or range or anything about this. This is a quadratic. We know quadratics and how quadratics work. And so we could just take 5 and plug it in. When we take 5 and plug it in, we get 25 plus 10 minus 3. 25 and 10 is 35, minus 3 is 32. Double check my numbers. I don't feel comfy with numbers. But that's it. That's all you have to do in that case. And notice I said in that case because it's not always going to be that easy. In fact, it will almost never be that easy. But let's try our second one. So that was number 1. Number 2 is the limit as t goes to 3 of t squared minus 5t plus 6 over t minus 3. Right off the bat, you should recognize you cannot just plug 3 into this, because if you plug 3 into this, you are going to get 0 in the denominator and you will be done. And so instead what we'll do is we'll try and see if we can algebraically remove this t minus 3 from the denominator. And turns out we can. We can factor. And so we'll rewrite limit as t goes to 3. Really, you should rewrite this limit until you evaluate it. Once you evaluate it, you no longer need to write the limit. But until you do, this limit should be continuing throughout the problem. And so this would be the limit t minus 2, t minus 3 over t minus 3. Which is the same as the limit as t goes to 3. Well, we could cancel those out of t minus 2. Now there's nothing preventing us from plugging that 3 in. And when we plug the 3 in, we get 3 minus 2. So this was an algebraic approach. We used algebra to try and clean it up. And the limit as t goes to 3 of this function ended up being 1. The next one is a little bit more complicated, but it's fairly similar. The next one is actually a difference quotient. And so it is the limit, let's see, number 3, the limit as h goes to 0 of x plus h cubed, or sorry, x plus h squared, making it harder for myself, minus x squared over h. Well, solving this one, we can't just plug the 0 in for h because we would get division by 0. And so our mission is to try and get rid of that h in the denominator. And so let's try expanding the numerator. We'll get the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared over h. We can cancel the x squareds, and then we can factor an h out, leaving a 2x plus h. Our h's can now cancel, and then we can plug 0 in for h because we don't have any issues plugging that 0 in anymore. And when we plug 0 in for h, we get 2x. This process where we take the limit of a difference quotient is called finding the derivative. And that is what chapter 3 is all about. But we're not in chapter 3 yet. And so we're going to focus on chapter 2 stuff for now. As I sip some coffee. Let's try number 4. Number 4 looks interesting. So 4 is the limit as t goes to 0 of the square root of t squared plus 9 minus 3 over t squared. Looking at this one, again, we cannot plug the 0 in because as soon as we plug the 0 in, we get 0 in the denominator. But we'd also get 0 in the numerator. So there's a chance we might be able to cancel that out somehow. The trick in this one, and it's a trick you should recognize whenever you see a square root, is see if you can use the conjugate. You remember the conjugate in this case would be to take the numerator and change the sign in that middle, basically making it a difference of squares. So t squared plus 9 plus 3 and t squared plus 9 plus 3. The numerator now will become, oh, and don't forget to rewrite your limits. I almost forgot. Limit as t goes to 0. So the numerator becomes t squared plus 9 minus 9 because it's a difference of squares and the cross terms will cancel out. On the bottom, it's gross. We'll just keep it gross. T squared over square root of t squared plus 9 plus 3. But now notice in the numerator, the 9's cancel, which means we can cancel out that t squared as well, giving us the limit as t goes to 0 of 1 over square root of t squared plus 9 plus 3. And you might be concerned because we still have a t in the denominator, But notice we can plug 0 into this now. And if we plug 0 into this now, we're going to get the square root of 9 plus 3. The square root of 9 is 3. 3 plus 3. Now we get 1/6 out of this. And looking at this starting function, you might not have recognized that as you're approaching 0, you're going to get 1/6. But it does. And that's kind of a neat behavior. Again, this was an algebraic approach because we were really applying algebraic techniques to try and simplify it. This next one is not going to have an algebraic approach. The only approach will really be to analyze the structure. And so number 5 is the limit as x goes to 0 of x squared sine of 1 over x. You can apply algebraic techniques as long as you want. You are not going to be able to make much headway on this. But what you can do is you can analyze the structure of this, because this is a trigonometric function. And so we can't plug 0 in here because we know that when we plug 0, we get a 1 divided by 0 in here. However, this is a trigonometric function, and we know trigonometric functions. I hope we do. And trigonometric functions, in this case sine is always going to be bounded between -1 and 1. And as we get to 0, this is probably going to be looking fairly chaotic, but it's going to be bouncing back and forth between -1 and 1. What happens to the x squared, though? Well, x squared is going to give us 0. What is 0 times anything between -1 and +1? And there's our answer. This problem is actually a special technique known as the squeeze theorem, because what's happening with this function is we're actually squeezing it between two graphs. Thinking of this function, if we were to graph it, we could actually graph it and it would end up basically being a sine function, which is bounded between x squared and -x squared. Since we know that this is bounded between -1 and +1, well, -1 times x squared is -x squared. X squared times +1 is +x squared. And so we know that that x squared times sine of 1 over x is going to be bounded between these two functions. The reason it's called the squeeze theorem is because no matter what this function looks like between here, it's got to be squeezed in that middle section. And at that one point where the two functions meet, we end up getting that y is equal to 0. And that tells us that the limit as we're approaching 0 is 0. That's our squeeze theorem. The next one looks to be algebraic. Let's take a crack at that one. So the next one is the limit as t goes to 0 again of 1 over t minus 1 over t squared plus t. With this one, again, we can't plug 0 in directly because we'll get 1 over 0 minus 1 over 0. And so instead, let's see if we can combine these. And it turns out we can. We can combine these fairly nicely. And so looking at it, we could get a common denominator, limit as t goes to 0, of t times t plus 1. And the second fraction already has that. For this first one, we would need to multiply the numerator and denominator by that t plus 1. But now we have t plus 1 minus 1, which gives you just t. And so now it's the limit as t goes to 0 of t over t times t plus 1. The t's cancel. And now when we plug 0 into it, we get 1 over 1, which is just 1. Not too shabby. One more problem to do for limits, and then we'll try a different type of problem. Number 7, again, this one will be more algebraic. This is the limit as h goes to 0 of 1 over t plus h minus 1 over t over h. Again, this is going to be a difference quotient. And so somehow we have to get rid of this h, which is in our denominator. Looking at this one, we have a complex fraction. And if you remember how to simplify complex fractions, this one will go very quickly. So this is limit as h goes to 0. The trick for simplifying a complex fraction is to multiply the numerator and the denominator by the common denominator. The common denominator in this case is t times t plus h. Multiplying through by that, limit as h goes to 0. For the first term, the t plus h's cancel, leaving t. For the second one, the t's cancel, leaving t plus h. Then on the bottom, we have h times t plus h. Distributing the minus sign, we will get the t's canceling. But then we'll be left with a negative h in the numerator. Our h's then cancel. And now we can plug the 0 in. When we plug the 0 in, we'll have negative 1 on the top. T just hangs out. And it's t plus 0. And so our final answer is negative 1 over t squared. And so that's how we would approach that one. And hopefully that's not too terrible. I think the hardest part about limits is that every single problem that we have done has had a different approach to solving them. And really it relies on your understanding of everything that has come before. Everything from Algebra 2, everything from trigonometry, and everything from all of your prior courses as well. It is all fair game. All of those techniques have been leading up to this. And now we have a massive toolbox filled with all these techniques, and we're going to need to use each one at a different time. Let's share the screen so that you can see this next problem. Now, this next problem is asking to sketch a graph. It says sketch a graph which has the properties, limit as x goes to 3 from the left of the function is equal to 4. The limit as x goes to 3 from the right side is equal to negative 2. F of 3 is equal to 1. The limit as x goes to 5 of the function is infinity. And the limit as x goes to infinity of the function is equal to 1. There's an infinite number of answers for this. We just need to come up with one. We want to create a single graph which has all 5 of these properties. And so probably the easiest property to do is going to be this third one, because that's just plotting a point. So let's create a graph. It doesn't have to be much of a graph. Looks like some of the numbers we're going to need is we're going to need a 1. We're going to need a, let's see, -2. We're going to need a 4, 3, 4. And then for the x values, we're going to need a 3. And we're going to need a 5. Then we don't care about the rest. So first things first, f of 3 is equal to 1. We can check that one off. Looking at these first two, they both are dealing with what happens as you approach 3. So as you approach 3 from the left side, we get something approaching 4. And we don't really care what it looks like, so squiggle, squiggle, squiggle. On the right side, it's going to be -2. And so we'll just do something like that. But the next one is at 5. As we approach 5, so now we've got these two checked off, we know that we need to get something approaching infinity. So we're going to have an asymptote at 5. And so this needs to go up. But not just that, it also needs to come back down, because for that limit to exist, it has to be the same on the left side and the right side. The last one is the limit as x goes to infinity must be 1. And that means that we must have a horizontal asymptote. Now, we can make this look a number of different ways. You could just go like this, but that's kind of boring. I usually do something a little bit more interesting, and I suppose that it turns into like a sine wave or something. The big thing is that it just has to get really, really close to it. It can go above and below that value, no problem, as long as in the long term, it approaches that value. And so this is an example of a graph which satisfies all 5 of those conditions. Next up, we have some limit laws. These limit laws are very similar to the limit laws we saw before, because sequences and functions really work very similarly. Most of the time, we ignore the sequences and just focus on the functions, because functions are a little bit easier to understand. The next section is really discussing some of these techniques which we've already seen and discussed. And so we'll do some of these, but we won't do all of them. And so these are some algebraic, and I think I might have thrown some analytic techniques for finding limits in here. So the first option, evaluate the function. For many functions, all you have to do is just plug the number in. And so if you have something which you know is a nice function, just plug the number in. For this one, we could just plug 5 in. For this one, there's no asymptote near E, so we could just plug E in and get a value out of it. That's always nice. Another is factor, simplify, and reduce. We've seen that. And so if you have a polynomial or some other function, often all you have to do is just factor it or simplify it. With this one, we can factor the numerator and the denominator, and it turns out we'll have an x minus 4 term, which cancels out. For this one, this is another difference quotient. If you expand it all of the way out, you'll be able to get most of the stuff canceling, and in the end, an h will cancel as well. The next one is to eliminate radicals. Often, the best approach to eliminate radicals is to multiply by the conjugate. We already saw one like that. With both of these, if you multiply by the conjugate, you're going to get the square roots disappearing. And so that's a very useful technique. The next one is the squeeze theorem. And the squeeze theorem is one which we talked about, where the function is basically squeezed between two functions. And this is a fun one right here. I mean, look at this function. It's horrible, horrible looking. The limit as x goes to 4 of x minus 4 cubed times cosine of 1000 over sine of x minus 4. Let's just look at what this second half looks like on our good friend Desmos. And so looking at this, let's say y equals, and then it was cosine of 1000 over, and then it was the sine of x minus 4. That is a beautiful graph. Look at this thing. And so when we're interested in figuring out what's happening around 4, craziness is happening around 4. Yeah, there's nothing very nice about what's going on here. But notice that it's being multiplied by x minus 4 cubed. And x minus 4 cubed, y equals x minus 4 cubed, goes to 0 at that point. If we throw that in here, we get a graph like this, which is hell on wheels just about everywhere on this graph, except as you come to 4. When you come to 4, this thing goes to 0. Note it says at 4 it's undefined, but everywhere nearby it is going to be 0, or very, very, very close to 0. So this function is being squeezed between two other functions. The two functions I think would be the absolute value of this, and then y equals negative absolute value of x minus 4 to the third. That gives you the top function and the bottom function if you look closely. And so that's our squeeze theorem. The next one is one which, I hate to say it, you're going to have to memorize. The limit is x goes to 0 of sine of x over x. And this gives you a hint for how it would be squeezed. 1 minus x squared over 6 is less than or equal to sine of x over x is less than or equal to 1 when you are near 0. Getting this 1 minus x squared over 6, it's a little bit complicated. It comes from something called the Taylor polynomial, which we are not doing anytime soon. But with this one, it's one which we can play with quite a bit. And so let's just look at what the graph y equals sine of x over x looks like. And again, at 0, it's undefined. But when we look at this, it looks pretty defined. I mean, the limit of this looks like it's going to be 1. And sure enough, the limit is 1. I would not recommend memorizing many limits because every problem is unique. But this is the one which I would recommend that folks memorize. The limit as x goes to 0 of sine of x over x is equal to 1. Because that one just keeps popping up throughout the semester. And there will be variations of that one. More algebraic techniques for finding limits. I mean, there's a lot of different techniques out there. But I do put this note, be careful. When you hear hoofbeats, think of horses, not zebras. What that means is even though a function might look messy, that doesn't mean you can't just plug the value in. And so looking at these, this first one, limit as x goes to 0 of 1 over x plus x over 2 over x minus x. You can't just plug the 0 in, but we could multiply top and bottom by x, and that'll clean it up very quickly. With this one though, limit as t goes to 0 of t cosine squared of t over t minus 1, you can just plug the 0 in. There's nothing special about this one. It's actually one of the easiest ones here. It's so easy that I put it as number 2 and number 4. But yeah, there's nothing really fancy to that one. For this one, limit as x goes to 0 of natural log of x squared plus ex plus the natural log of 1 over x. This one you could combine into a single logarithm and try and figure it out that way. Although I would be cautious about this one though, because I believe the answer does not exist, because the left side and the right side will not match up, because I don't think this function is actually defined for negative values. And so be careful of that. Remember what the limit actually means. And then there's this one. And this is where I said knowing the limit as x goes to 0 of sine of x over x equals 1 could come in handy. Because what if you had something like, let's do number 3. The limit as t goes to 0 of sine squared of 3t over t squared. Well, notice that this is almost like this, but not quite. And so let's see if we can make it so that it's closer to it. If we were to expand this out, we could say that this is the limit as t goes to 0 of sine of 3t over t times sine of 3t over t. Again, this looks similar to this. The difference is that 3. And that 3 kind of makes a big difference. Really what we would need is we would need whatever this thing is in the top to match whatever this thing is in the bottom. And so if we have a 3t here, we would need a 3t in the bottom. And we can multiply by 3 on the bottom as long as we multiply by 3 on the top. And we can multiply by 3 on the bottom as long as we multiply by 3 on the top. Now this bit goes to 1, and this bit goes to 1, and we have 1 times 1 times 3 times 3 is 9. So the limit as t goes to 0 of sine squared of 3t over t squared is 9. And so these are some fun problems which you should definitely play with and make sure that you feel comfortable with. But they're just using the known limit laws. And really, you can just play with these a fair amount. Looking at this one here, the 4, if you divide the numerator and the denominator by sine of x, you should get a lot of stuff canceling out. And looking at this one, I think if you multiply by the conjugate, and so you multiply everything by cosine of t plus 1, then you can use your Pythagorean identity to convert it into a sine squared. And so these are techniques which we have from prior courses. We just have to be able to apply them in these situations. Excellent. So that brings us to the end of the talk about limits. The last piece of the puzzle for chapter 2 is the idea of continuity. And so continuity, it works the way you would expect it to work. And so a function is continuous at the point x equals a if the following 3 things are true. And before we even get to those 3 things, let's just talk about the big picture idea of continuity. A function is said to be continuous at a point if you can draw a curve, or if your function can be drawn as going through that point without lifting the pen. And so notice when I drew this, I drew it and I did not have to lift the pen in order to get that point on there. If we had a graph like this, notice you cannot draw this function without lifting up your pen and putting it back down again. Same if we had something like this. How about this one? And then how about this one? This one has 2 spots. One is an infinite discontinuity, and one of them is a jump discontinuity. This is a step discontinuity, I believe. I always forget the names. But there's different classifications for discontinuities. In other words, points where a function is not continuous. For something to be continuous, though, we have a checklist. And here is the checklist. The function must be defined at that point. If it's not defined at the point, then it's not continuous at the point because there's no point there. The second one is the limit must also be defined. And remember, the limit being defined means the left side and the right side need to match up. And then the third one is the limit has to be equal to the function. Basically, 1 and 2 must be equal. If that's not the case, then the function is not continuous. A function is said to be continuous on an interval AB if it is continuous at every point on the open interval. A discontinuity is a point where the function is not continuous. And so the function is said to be discontinuous for that value. And again, the easiest way to think about it, can you draw the graph without lifting your pencil? Looking at this example, it is discontinuous at -2. It's discontinuous at 2. It's discontinuous at 4. It's discontinuous at 6. And then the function ends at 8. With this one, it's discontinuous at -4, at -2, at 2, and at 4. At 0, we have a cusp, which means the left side's coming up and the right side's coming up, and they're meeting at a point, but it's not as smooth as we might want, but it's still continuous. I mean, you could draw that without lifting the pencil. And so -4, -2, 2, and 4 is where it is discontinuous. The nice thing is most of the functions we've played with so far are continuous on their domain. And so the following functions are continuous for all real numbers: polynomials, exponentials, sine and cosine functions, absolute values. They are continuous everywhere. They are nice, smooth functions. Well, the absolute value is not smooth, but that's another story. The following are functions which are continuous on their domain. And so when they're undefined, we have to be careful. And so rational functions, radical functions, they're only defined for positive values. The trigonometric functions, well, sine and cosine are continuous everywhere, but the others are not. And logarithmic functions are only defined for positive values. And so for each of these, we can ask the question, when is the function continuous, or where are the discontinuities? And looking through these, we can actually just kind of look through where the functions go wrong. And so for number 1, 2x e to the x, there are no points where this function goes wrong. It's a polynomial or even a linear function times an exponential. There's nothing wrong with this. It's continuous on its entire interval. For number 2, well, we have a denominator here. And if the denominator is ever equal to 0, that tells us that we are going to have a discontinuity. And our denominator is equal to 0 at +2 and -2. For number 3, we have the natural log of the absolute value of x minus 3. Natural log is continuous for positive values, and this is positive everywhere, and so that's not going to be a problem. The only problem is that when x is equal to 3, we get the natural log of 0. And natural log of 0 is undefined. And so for this one, it's continuous everywhere except when x is equal to 3. For number 4, the numerator is fine, but we have a denominator. And remember, denominators can not be equal to 0. But good news, 2 plus cosine of x is never going to be equal to 0. And so this function is continuous for all real numbers. There are no discontinuities. For number 5, really you just have to figure out where the function is defined. And so the function is going to be defined, let's see, between -10 and +5, is that right? I'll let you look it up. Graph it and you'll see it real quick. For 6, we have a couple of things going on. The numerator, we have the natural log of an absolute value, and so that's going to be similar to 3, which tells us that x cannot be equal to e. In the denominator, well, x squared pi to the x minus 9 pi to the x, we can factor that. And when we factor it, we'll get a pi to the x times x plus 3 times x minus 3. The pi to the x will not present a problem, but at x equals 3 or x equals -3, we'll get 0 in the denominator. And so for number 6, x cannot be equal to e, but x can also not be equal to 3 or -3. At those 3 values, we are going to get discontinuities. 7 is gross because cosine of x minus 1 is going to be 0 an infinite number of times. For 8, we have the 1 over x, and we can't have 0 in the denominator. And then for number 9, what's interesting about this one is it's actually going to be defined for all real numbers. We have a denominator. We can't have the denominator be equal to 0, but we're never going to get 0 in this denominator. We can have sine be 0, we could have cosine be 0, but they'll never be 0 at the same time. The more algebraic problems are these, though. So find a value of k that will make the following functions continuous. And let's do one of these. I don't know that we need to do all 3 because once you see one, you've seen them all. And so let's suppose that we have f of x is equal to x plus 1 squared and 2x plus k. So it'll be x plus 1 squared on negative infinity, comma 2, and 2x plus k on 2, comma infinity. And we want to know what value of k will make this function continuous. Well, we know that this is continuous everywhere. We know this is continuous everywhere. The only place we have to worry about is at the value 2. Because at the value 2, we go from the first equation to the second equation. And so all we have to do is plug 2 in, which will give us 2 plus 1 squared equals 2 times 2 plus k. And so all we did was we just took 2, we plugged it in for x, and now we can solve for k. 2 plus 1 is 3, 3 squared is 9, equals 4 plus k. That tells us k is 5. The others are very similar. And so share the screen real quick. In this case, we only have to worry about 1. And so we can plug 1 in, and we'd get e to the -1 is equal to 1 squared plus k. And then you just have to solve for k. With this one, looks grosser, but you're just plugging 3 in for x. And so pi cubed, ln of 3, sine of square root of 3 plus k. Solve for k. The last thing we have today is the intermediate value theorem. And the intermediate value theorem is a very nice and useful theorem, and it's very, very conceptual, but there's not many math problems we can ask related to it, because the answer is always going to be the intermediate value theorem. And so what the intermediate value theorem says is, suppose that a function is continuous on a closed interval, and let n be any number between f of a and f of b. Then there exists some number c on that interval such that f of c is equal to n. Let's show what this physically would look like. And so let's suppose that we have some function, and we don't really care what this function looks like. There we go. It's going from a to b. And then this is going from f of a to f of b. What the intermediate value theorem says is if we choose any value between f of a and f of b, let's say that we choose this value here to be our n, then there's going to be at least one point on this function which is going to be giving us n as our output. And so in this case, we actually have like 3 values. We have one here, one here, one here. Does not matter which one you choose. If this value is c, then we have the property that f of c is equal to n. And so no matter what value you choose between f of a and f of b, provided this was a continuous function, there's going to be some value on this interval which gives you that y value out. The reason the continuity is required is because if this were a discontinuous function, something like this, well, then it's no longer true. If this function is continuous, though, well, there's got to be some way that it's going from here up to here. And at that point where it's crossing, that's going to be our c value. That's the big picture for the intermediate value theorem. And the reason I say we can't really ask many questions related to it is because the answer is always going to be the intermediate value theorem. Case in point, consider the function f of x equals the natural log of absolute value of 1.2 plus cosine of x. Explain in words how we know that there is some value a on the interval 0 to pi where the function is 0. And the 3-word answer is the intermediate value theorem. I guess that's 4 if you include the, but yeah. If we check this, when we plug 0 into this function, we get the natural log of 1.2 plus 1, which is greater than 0. If we plug in pi, we'll get the natural log of 1.2 minus 1, which is less than 0. Since we're going from a value which is greater than 0 to a value which is less than 0, we can see that the function has to cross at some point, because this is a continuous function. It's a composition of continuous functions. And so since it's continuous and it goes from above to below 0, we get that the intermediate value theorem says that it must at some point attain that value. And that's it. That brings us to the end of today's lesson. And so when we look at what we did today, we did a lot. Chapter 2 is a very critical part of this course. When we think about calculus, calculus is often focused on derivatives. Limits are a tool that get us to derivatives. Remember those problems where we were dealing with difference quotients? Well, the limit of a difference quotient is a derivative. Our derivatives will then give us antiderivatives, which are also known as integrals. And those concepts get us all the way through chapter 6. So the majority of this course is going to be based on the underlying principles of limits. That said, as I'm sure many of you have seen, limits can be difficult to calculate because there is no one set approach to solve them. When we were doing these, every single problem was a little bit different, and many of them relied on your understanding of the structure of functions. And so you really need to be able to analyze those structures. Make sure you understand the base functions, but then ask questions about what happens when you do the compositions of those functions, or the ratios or products or sums of those functions. As we saw with these, the products versus the sums versus the quotients, they can have very, very different behaviors. And you want to be able to understand those behaviors. We then did limits at infinity. We did limits at individual values. We talked about some guidelines to kind of help you along the way. But really, every problem is so unique that you really need to be able to pull from your entire algebra tool set and your understanding of them functions. We then talked about continuity, and continuity, it's a nice thing. It's very easy to understand because it's all about just, is it a nice smooth curve or not? And if it is, it's continuous. And if it has a jump or a skip or something weird going on, then it's not continuous. The only thing to be careful of is cusps, and cusps are continuous. Turns out they're not differentiable, but that's chapter 3. And then we ended with the intermediate value theorem. And so, as always, you have a tremendous amount of homework to do. And so I hope that you all go out and get your homework done, and you will be all set. Take care.